Welcome to the presentation of my master thesis. My name is Marlene Meyer and I have studied neurocognitive psychology in Munich. The present thesis is a collaboration between the University of Birmingham and the Ludwig Maximilian University Munich. It is called Improving Eyewitness Discrimination Accuracy, Comparing a Novel Interactive Lineup Procedure to Photo and Video Lineups. You might already be familiar with the interactive lineup procedure, therefore I will keep the explanations short. In Birmingham, a new simultaneous interactive lineup procedure has been developed to enhance discrimination accuracy and is currently tested in contrast to existing procedures. What is special about this procedure is that every lineup face can be turned vertically from left profile to right profile by mouse click. So an interactive lineup offers the participant to actively see the lineup face in any position from -90 degrees to 90 degrees. In a recent study of Koloff and colleagues, the sequential interactive lineup procedure has been shown to improve discrimination accuracy compared to sequential static photo lineups, and simultaneous interactive lineups yielded better lineup performance than sequential interactive lineups. In another study of Koloff and colleagues, discrimination accuracy is facilitated when encoding and retrieval pose match, and subjects seem to automatically reinstate perpetrator pose to aid memory retrieval. So, to further test this novel interactive procedure, the present study addressed the outstanding question of whether a simultaneous interactive lineup procedure enhances eyewitness discrimination accuracy compared to two widely used procedures in laboratories and police forces across the world. The simultaneous frontal pose photo lineup, which is common in the US, and sequential video lineup, which is the most widely used procedure in the UK. And additionally, we investigated whether discrimination accuracy on the lineups depended on the encoding field. We hypothesized that the interactive condition would show higher discrimination accuracy than the video condition based on the diagnostic feature detection theory. In the simultaneous interactive lineups, participants are able to discern facial features that are diagnostic of guilt and facial features that are non-diagnostic. Diagnostic features are the ones that differ between target and filler faces, and non-diagnostic features are the ones that are the same between filler and target faces. Then participants can consciously emphasize the diagnostic characteristics and disregard the non-diagnostic features. This results in an improved ability to discriminate between faces that have and have not been seen before. In contrast, sequential video lineups theoretically make the direct comparison of faces more difficult because the diagnostic facial features are not emphasized. As a consequence, participants could base their decision considerably more on the non-diagnostic features, and then discriminability is deteriorated. The unequal variance signal detection model gives a theoretical explanation for this. It is illustrated in the figure of Wixit and Mickels, and the model indicates how face memory strength is distributed across guilty and innocent suspects. There is one target distribution and one lure distribution. And one main assumption is that a decision criterion is placed at some point on the memory strength axis, and a suspect identification occurs if the memory strength of a face exceeds it. And the different lines with the different numbers conceptualize confidence ratings. For example, one could make a decision being very unsure for 1, whereas another one could make a decision being very sure for 5. And the correct identification rate is represented by the proportion of the target distribution that falls to the right of the decision criterion, and the incorrect identification rate is represented by the proportion of the lure distribution. The discrimination accuracy is shown by the degree of overlap between both distributions. The more overlap, the less participants are able to discriminate between target and filler phases. In our case, we would assume that the interactive condition is represented in procedure A as the more diagnostic one, and the video condition in procedure B as the fairer diagnostic one. And the figure also illustrates the connection between ROC curves and the signal detection interpretation of discrimination accuracy. A ROC curve consists of multiple hit rate false alarm rate pairs. And this is over different confidence levels. And the hit rate false alarm rate pair for each confidence levels are represented as dots. The most left pair of the ROC curve represents all lineup decisions, so all hits and all false alarms that were made with 100% confidence of the participants. And the next pair of the ROC curve would then represent all lineup decisions made with 90% or higher. And a lineup procedure shows better discrimination accuracy compared to other lineup procedures when two criteria significantly differ from the values of the other procedure, and this is a higher hit rate as well as a lower false alarm rate. And this is then illustrated in a higher ROC curve. So the interactive condition should result in a higher ROC curve than the video condition. And in addition, we hypothesized that the interactive condition would show higher discrimination accuracy than the static photo condition in the profile encoding condition based on the encoding specificity principle, since it is a common finding that face recognition accuracy is viewpoint dependent. In the static condition, participants learn the faces from the profile view, but are needed to identify them from the front view in the lineup, while in the interactive condition, participants are allowed to rotate the lineup faces into the profile position from the learning phase. So when the viewing angle at encoding and retrieval are the same, discrimination accuracy should be improved. We conducted a face recognition lineup task in which participants learned target faces and were tested using a lineup. We decided to use a face recognition lineup task instead of a typical eyewitness paradigm because the recognition lineup paradigm provides multiple data points instead of just one data point per participant. Also, the conceptual replications that use the recognition lineup paradigm are in keeping with the studies that have used the eyewitness paradigm. So participants were shown a list of 12 faces, each presented at once for 5 seconds, and were instructed to pay attention as they were asked questions about them later. And to test the influence of encoding view, participants either saw their target faces only from the front or only from the profile view in the learning phase. After engaging in a distractor task, they were randomly assigned to a 6-person simultaneous static photo lineup, a simultaneous joint movement interactive lineup, or a sequential video lineup condition. In the figure in panel A, you can see the static photo condition in which 6 faces were presented simultaneously in frontal pose. In B, you can see the interactive condition in which 6 faces were presented simultaneously in frontal pose, and the participant used the computer mouse to click on one face and rotate it. Then all faces moved jointly together. In C, you can see the video condition in which only one face was presented at a time via video, in which the face moved fluidly from front to profile to the opposite profile and back to the front. Each participant was tested on 12 lineups, with 6 of them being target present as well as 6 target absent lineups. Also, for each lineup, participants were required to give confidence judgments about their lineup identification decisions. Now coming to the results. In the graph, you can see the partial ROC curve and the partial areas under the curve statistics for all 3 conditions: simultaneous interactive, simultaneous static, and sequential video lineup. The front encoding condition is represented in the upper row, so in A and B, and the profile encoding condition in the lower row, so in C and D. The ROC lines of best fit were plotted from numbers estimated by unequal variance signal detection models. So next to the ROC analysis, we fitted a signal detection model, which showed the same results as the ROC. And chance level performance is indicated by the dashed line. At first glance, the interactive conditions seem to be the best condition because it shows the highest ROC curve. So, but to test whether the differences in the ROCs were statistically significant, we calculated POC in both encoding conditions, so for front as well as profile encoding conditions. The POC for the interactive condition was significantly greater than the POC for the static photo and for the video condition. And there were no significant differences between static photo and video conditions. The current results are in line with the diagnostic feature detection theory, which can account for the finding that interactive lineups showed a higher performance than video lineups. And in addition, the superiority of the interactive condition compared to the static condition is predicted by the encoding specificity principle for profile encoding condition, since it is a common finding that face recognition accuracy is viewpoint dependent. But why is the interactive condition also better than the static photo condition in the front encoding condition? This result is in line with the study of Koloff and colleagues, who found improved discrimination accuracy in sequential interactive lineups compared to sequential static photo lineups. The active exploration account provides an explanation. So actively exploring faces instead of just passively perceiving faces has been shown to enhance memory performance in face recognition research. Therefore, participants in the interactive lineup condition could have benefited from actively engaging in the lineup compared to participants in the static photo lineup condition who passively saw the lineup. So in conclusion, the present study highlights the importance of improving existing lineup procedures. The recently introduced simultaneous interactive lineup procedure demonstrated an increased identification of target faces while concurrently reducing the wrongful identification of filler faces compared to simultaneous static photo lineups and sequential video lineups. Interactive lineups especially enhance discrimination accuracy when the viewpoint of the faces differs between encoding and retrieval. Since eyewitnesses likely have seen the perpetrator from another perspective than the front, the interactive lineup procedure enables them to actively interact with the lineup according to their memory. Therefore, police should consider the encoding view in practice, which is the reason why the use of the simultaneous interactive lineup procedure can be recommended. Future research could further build on this by replicating the present results using a standard mock crime eyewitness paradigm. Now coming to an end of the presentation, I would like to thank you for your attention, and I would like to thank Melissa Koloff, Heather Flo, and Tobias Staudigl for an incredible supervision and ongoing support during this whole master thesis project.